then you get something. And I observed the Wheel of Fortune, and I made an assumption that any number that has been seen recently is less likely to come the next time. That's a reasonable assumption, right?
No.
So for example, if, let's say, they roll it and you get 7. They roll it again, then you get 7. So the next time is very unlikely that it will get 7, right? You don't seem to buy that. So I found out that what happens is that I try to remember what was the previous outcome, and then somehow the scheme didn't work. And the reason was that every roll was independent. So whatever had happened previously, it has nothing whatsoever to do with the outcome of the next time. So because everything was statistically independent, if they are A and B, so outcome of the first roll of the Wheel of Fortune, outcome of the second roll of the Wheel of Fortune, they are statistically independent. So so this relation holds. Okay, now here's so if you toss a coin, then let us say you toss a coin and 5 times you get head. So 6th time you toss it, what is the probability that you will again get head? It is still half. So it's because there is statistical independence, right? And okay, let me ask you a question. Let us say 2 events are disjoint. 2 events are disjoint. Does it mean they are statistically independent or not? What do you think? 2 events are disjoint. Then, does that mean they are statistically independent? But I'll give you a few minutes to think about it, and we'll come back to the question. And it is actually not an easy question. Now there is a common approach that is often used. Let us say we have an event A, which you can divide into disjoint pieces. If event A into disjoint pieces, and those disjoint pieces are, let us say, A sub I equal to 1 to n, then we can write for probability of B summation over values of I, probability of B given A sub I multiplied by probability of A sub I. This is a very useful expression. We are not going to prove these things, but this is one of the very useful expressions. Okay, so let's come back to the question. 2 events are statistical. 2 events are disjoint. Are they statistically independent? Okay, how many of you think they are? If they are disjoint, that means they are independent. Okay, why?
I can't think of the other side. I mean, this is just intuitive. I don't.
Okay. Would someone say the other way? Would someone say that if 2 events are if 2 events are disjoint, then they cannot be statistically independent? Would anyone say that? Well, you should. Because if the 2 events are disjoint, that means if A happens, B cannot happen, right? That's the definition of disjoint. If A happens, B cannot happen. And if they are disjoint, they cannot be independent, because outcome of one would affect the outcome of other. So if you know that A has happened, then B cannot happen, so they obviously cannot be statistically independent. So two events can be statistically independent only if happening of one doesn't affect happening of the other. So you need to be careful about these two concepts, disjoint and statistical independence. Okay, so you probably may have seen this before. It's used in a number of calculations. Okay, let's then come to random variables. Okay, so let's take a look at random variables. And so a random variable is something that takes a specific value at a time. So for example, let's say if I randomly pick a student in a campus and get his height, and so the random variable could be x. So x is the height of a randomly chosen student, and it is possible that a specific value, so this is a random variable, so that means this is a variable that changes but randomly, and then you can have a specific value. Let's say I pick a specific value, and so I pick a student, and maybe the student is 5 feet 10 inches. So this is a specific value. And it is necessary in whenever you are doing any probabilistic methods to distinguish between a random variable and a specific value of a random variable. So sometimes what they do is they will have, this would be in bold, and this would be not bold. So this, when it is not bold, it refers to a specific value. When it is bold, it refers to it as a random variable. But of course, since I'm writing on the board, so I cannot make bold, so I will, somehow, it should be clear from context. Now a random variable, this is the usual abbreviation, is defined by its density function. If you know the density function of a random variable, you know everything about the random variable except a specific outcome, of course. And a random variable, it could be discrete or could be continuous. And here are some common ones, some common distributions. No, I'm sorry. Some common things from theory of probability. So let's have the density function here. Density function. And often density function, it we represent this way. When things are continuous, then this refers to probability that random variable x is between two values which are some x, and this is lowercase x, and x plus dx, where uppercase x indicates the random variable, and lowercase x represents a specific value, and discrete we would sometimes specify this way. Probability that it takes a discrete value x of I. And then we have the cumulative distribution function. Cumulative distribution function, in short, which is sometimes referred to as CDF, is actually often referred to as CDF, which is this. And for a continuous random variable, it goes from whatever is the minimum value of x defined to some specific value. And in case of discrete, it goes from I equal to whatever is your minimum I to some other I. I think I need to have something here. Okay, to be consistent. Okay. J equal to some minimum value of I to some specific value of I, just to be consistent in terms of mathematical notation. And we have a couple of minutes about the expected value, the mean. Which is often referred to as EX. And of course, to take the mean, you would do this. For the range for which the random variable is defined, this will give you the mean, or equivalently, I suppose I should, to be consistent, call it J. I suppose I can use I here. That should be okay. Oh, sorry about that. So this is, so you need to know about the density function. A density function, or, now if you know this, then you know this. If you know this, you know this. You have to know one of them. Density function or the distribution function. So this is the cumulative one, and this is the non-cumulative one. And here's the expected value, where you take the values and multiply it by the appropriate weight, and take the average. So expected value is, in some way you can call it weighted average. So we will continue our distribution. So next time we are going to look at some of the distributions, and then we are going to look at stochastic processes that form the basis for some of the reliability calculations that we are going to be doing. And so the quiz is available
And